Cannot.
Okay, to begin, we're going to do a quick recap of what we've learned in our previous lesson about refraction, about bending of light. Here, let's do a quick test. You have media number 1, media number 2. Supposing media number 1 is water. Media number 2 is diamond. I have one ray of light coming through water. I draw a normal. How will this light ray bend? Towards or away from the normal? Okay? How do you tell, right? Wait, I hear the front. I want to see the back. Okay, so when light passes from water to diamond, using this piece of information here, how will it bend? Ryan a round of applause. I don't remember.
Wasn't a very straight line then. What a straight line. What a straight line.
You go back to high school, you do that again.
Good job, Brian.
How will you go about answering this question? And I will always provide this table. Yeah? I don't expect you to memorize this. But how might we make use of this information? You see the word refractive index? Refractive index is a measure of how optically dense an object or media is. The larger it is, the more optically dense. Smaller, the less optically dense. Here we have a light ray traveling from water, which is 1.30, diameter 1.38. It's traveling from less optically dense to more optically dense. How should light bend? Where can you find this piece of information? Which page of your textbook? I see some of you have highlighted. Yeah. So which page? Which page? Which page you left? Well, yeah. Next, maybe everyone refer to page Rushin just said. Page 12 gives you the clue. When light travels from less to more optically dense, it should bend towards the normal. Yeah? Okay, so Brian, what Brian has done, he has bent away from the normal. Light wave should bend towards the normal. Just like the practical you just did yesterday. You made it travel through air into glass. We check over there, air is 1.000, glass is 1.5. And that's what we observed yesterday, right? All the light rays always bend towards the normal. You always find that the angle of incidence is bigger compared to the angle of refraction. Okay? So that is the main learning point we had in our previous lesson as well as in our previous practical. Today, we're going to dive a little bit deeper and see how we're going to draw ray diagrams to explain certain phenomena that we observe in real life. First and foremost, I'd like to share how scientists calculate this refractive index. Refractive index is actually calculated through this equation. You can find this equation in your textbook too. On page 13, you should be able to see this equation. You box up the equation. Use highlighter, use pen, use star it. Okay, this is the equation we use to calculate all your refractive index. I'm going to be a bit lazy. So refractive index in bracket n equals to the speed of light divided by the speed of light in the medium. Even instruments, they can measure the speed of light or the speed at which light travels. If we go back to the table, you see that the refractive index of glass is 1.5. Assuming n is glass, how would scientists have calculated the refractive index of 1.5? They would have calculated it by taking two measurements. The first measurement is to measure the speed of light in air. Then they will use the same tool to measure how fast light is traveling within glass itself. So once we have the two speeds and we take them divided by each other, we'll be left with the refractive index. Notice that the refractive index has no units. It has no units because if you take speed divided by speed, there won't be any units. Just like if you take meters divided by meters, you kind of cancel out the units. Okay? So you don't expect to find units for the refractive index. It's not wrong, it's supposed to be like that. You are expected if we were to provide you two different speeds. Let's say we provide you the speed of air, then we provide the speed of glass, we ask you to find the refractive index of glass to be able to calculate. Today we're going to move on to some ray diagrams. The first ray diagram we're going to draw helps us understand why we see things a certain way, especially when you place them in water. at the. Are you okay, Joe? Good job. Good job. Have you ever experienced this? When you have a cup, maybe that day was in fact when you were doing our refraction experiments, one of the experiments require you to place a coin at the base of the cup. You stand at an angle where you cannot see the coin at all. Okay? If you were to try to see, you will not be able to see the coin. But as you started to pour more and more water in, eventually you could see the coin. Why is that so? That's because there's a little bending of the light at the edge of the water. That allowed you to see the coin. And in fact, the coin looked like it has risen from the bottom of the cup, as though it's floating a little bit. We're going to investigate how this phenomenon happens using ray diagrams. We call this apparent depth. It's spelled apparent. Oh, it's a E. We say apparent because even though we observe the coin to be higher, this is not the actual depth. Our eyes have been tricked. Our eyes have been tricked because light bends at the waterfront. In reality, the coin is still at the base. But however, we perceive the coin to have risen because light bends. So today we're going to draw some ray diagrams to help explain why we end up seeing the coin or whatever object rising to the surface, even though it's not the case. In real life, if you were to take a boat sometimes, and the boat travels across a clear crystalline water, not crystalline, crystal clear water, you may observe that hey, the fishes look like it's very close to the surface. Reach in, actually they are still quite deep underneath. A lot of things appear apparently higher than it seems. Why is that the case? And that is what we're going to investigate and begin to draw. I'll need you to go to this page of the textbook where you can see a fish as well as a rectangle over the edge of the water. That's on page 15. If you're on page 15, this is what you should see. Okay, on page 15, this is what you should see. You should see it's like a cliff. There's a human at the edge. This human, for some reason, is rectangular in shape. Okay? I cannot take it. I'm going to make a humanoid shape. Okay. Now put this person's eyes at the edge up. Okay, give me a nose. Okay. Susan's chest is a bit depressed. Huh? Here we have a person. He's at the edge of the water. What else does your diagram show? Then there's the waterfront over here, and then there's a fish beneath. This is what you have. I'm going to teach you now how to draw a ray diagram to explain why the image of the fish appears higher in the water than it actually is. Okay? Now I need you to follow the steps along with me. Our brain is often tricked. Even though the fish is at depth, our brain is often tricked to believe that the fish is higher than it actually is. Today we're going to learn how to draw a ray diagram to explain that. It is tricked because, in reality, the light ray bends over here to enter our eye. But our brain thinks that light rays must travel in a straight line, that it cannot bend. Our brains cannot overcome that, this piece of information. So instead, even though the light bends at this point to enter our eyes, our brain will still think that the image will end over here. Because our brain still thinks that light rays travel in a straight line. That is the problem that our brains cannot overcome. So that's the image, that's the ray diagram we're about to draw right now. You should see this particular image with you. First and foremost, I would like you to decide where the eyeball of the person is on your rectangular block. So in this particular case, you could draw an X to fix the position of the eyeball. Will everyone do that now? No. I mean, you can put it higher, but not too low. Nobody's eyes is at the belly button. On the feet, yeah? So, position the eyeballs a little bit higher. Goodness. Something really great. Yes. For what? Don't like what? Oh, you don't like the back of your head being put like camera.
Bring the camera forward.
Okay. I don't have a good response to this at the moment. I will think of a better response in time to come. If not, I'm going to have this whole row over here. I want to shift that in corner. I promise you, I will not identify your name as much as possible. Okay. Anyway, all these videos is unlisted, so you cannot possibly search for it on YouTube. Only you have the link. Only the person with the link can view the recordings. Yeah. So they contact your. You cannot search on YouTube. You cannot search 105 refraction lesson. It's impossible to find. Okay, everyone, position the eyes. Okay, mark it with an X. Once you position the eye, the next thing we will do is we will draw a light ray coming from the tip of the fish. So how will I do this? I demonstrate to you first, yeah? First and foremost, what should happen is that you have a light ray traveling through the water from the tip of the fish to the surface of the water. When I draw this, I'm not trying to say that the fish is shooting lasers out of itself. What I'm trying to show you is that when light rays strike the fish, some of it will bounce off the fish into your eyes. That's how you see. Okay, the fish is not shooting lasers. Next thing you will draw, I'd like you to then connect the dot, connect it to the person's shucks. That means connect it to the person's eyes. I think I need to work backwards. Okay. Here you notice that the light ray doesn't quite travel in a straight line. It will bend a little bit. So this is what it could look like. I think the problem with my fish is that the fish is a bit too close to the edge. Now I'm going to shift my fish a little bit so that it's more accurate to you. For those that are a bit faster, you want to go ahead, please continue. I think that my fish should be a little bit further. I'd like you to try your best when you draw this. The angle of incidence versus the angle of refraction. Because this is water, by right, this angle of refraction should be smaller than the angle of incidence. Don't need to measure, but it should look smaller. So I say again, the angle of incidence should be bigger than the angle of refraction. This is what we've learned. When it travels from air to water, something from more dense, less dense to more dense, this should be the case. Sorry, I would like to say I think I made a mistake also on the whiteboard. In reality, if the light ray is traveling from water to the eyes, that means we need to flip our perspective. Now, this is the angle of incidence, and this is the angle of refraction, because it's the direction light is taking. Okay, so I labeled the things wrongly. In this particular instance, the angle of incidence is smaller than the angle of refraction. This is what you should be drawing. That confuse you there? Okay. If I had drawn the image going the other way, so let's say from the human to the fish, we all agree, right? If it's traveling from air to water, the angle of incidence versus the angle of refraction, this needs to be smaller, right? Because it's traveling with something more dense. However, if we go the opposite way, which is this way out, we are actually traveling from more dense to less dense. So if we travel from more to less dense, it should bend away from the normal. Okay, so that is the logic here. So this is what you should be doing. May I get everyone to do now? Some of you are very fast, you're done already. Could I also get you to insert in the normal, draw in the angle of incidence and refraction, so that you can prove to yourself that one is bigger than the other. When possible, always use pencil when you're drawing, because we are human, we make mistakes, sometimes we incorrect. Okay, next step. Therefore, where will the tip of the fish appear to be to the human being? Yeah, the problem is humans think that like our brains will perceive the light travel in a straight line. The human will think that the fish is higher than it actually is, at the same time slightly shifted forward. So this is what you do. I would like you to extend out this light ray using a dotted line. Make sure it's straight. Then I would like you to redraw this fish. If this fish is around, I don't know how many cm, x cm, you can measure out for yourself. The image you draw of the fish should be also around x cm. Okay? I would like you, however, to take note. The image of the fish needs to be slightly shifted forward and definitely higher up. This is the image of the fish. I'm going to represent it with eye for the image. It's not a real fish. This is where the fish appears to be. Okay, so what would it look like on the screen? This is what it looks like. You can follow the screen or follow me. Now just go around and check where your fish is. Should be higher and slightly forward. Where your fish has one in the box. You know, draw a fish. Try. Okay. You know, your fish is slightly backward. Oh yeah. Yeah. Why? I think you try your best because of the way you draw it. The best you can do is to take a stop there and you draw. Okay, very good. Okay, to complete this whole diagram, we're going to draw one more light ray, but this time from the tail of the fish. Oh, can you draw in a different color? Please go ahead if you really want to. Okay, so to the human being thinks that he's viewing the image in a straight line. So I'm going to draw a straight line, then dot. Okay? So this is how he thinks he's perceiving the fish. In reality, light bends. So that means from here to the tail of the fish, this is how the light actually travels. It travels upwards, it bends at the surface of the water towards the eye. If you were to draw the normal, you should also see the same thing. Oh yes, my com died. Oh, he died. Okay, try to get everyone to do this. We draw one more light ray. This light ray is to show how light travels from the tail of the fish up to the eyes. So I recap the steps. The step you should take is you draw one straight line from the eye all the way to the tail of the image of the fish. But this part you should make it dotted. After that, from this part where it intersects the water, you bend the light back to the fish tail.
Where did my thing go? You. Where's my pin? What do you mean you don't know?
If you are all good, now we try a question from the RE, because 7.2. We do now, then you have one less part of the RE as homework. I present to you almost exactly the same question. Now try from start to end this entire process. So 7.2, you look at page 4. This question is testing you on how the apparent image is formed. I'd like you to flip to page 4. I'd like you to try the same steps from start to end. How you're going to show the teacher why the image of this particular dolphin appears higher than it actually is. Okay, I'm just going to maybe number the steps. So you can start off with this line over here, followed by the second line to the eyes. Third step is to draw the dotted line to the tip of the dolphin. Fourth step is to draw a straight line to the tail. Step number 5 is to draw one more final light ray from the tail to the edge of the water. Okay, if you follow the steps, you should be able to answer this question. Then you have one last question. Okay, 7.2, question 4. Yeah, correct. I only asked you all to do those questions, but now since you learn this, let's do on the spot. You have less to do. Where's yours? Everyone use a pencil. I don't want to see you using pen again. Huh? Use a pencil. Very fast. Okay.
Very good, very good.
Okay. Okay. A little bit my bad. I think the question asks you to solve this puzzle instead. They're asking you from the dolphin's perspective now. How would the dolphin see the child? Where would the child look like it is? Okay. It's okay, use pencil, right? what will it look like to the person? Make sure you use a pencil since we are all experimenting. Oh, the trial, you can try your best, draw one head, draw one body. It is quite challenging. Try to imagine things from the perspective of a fish now by the same steps. So now you need a light ray going from the tip of the person's head to the fish's eye. How would that light ray travel? To work backwards. Where will the person appear to the fish? Definitely meet somewhere in the air, but will it be closer to the person or further away from the closer to the fish or further away from the fish? Okay, you try. Where would the virtual image of the drop be? Okay, drop. Okay. now kind of floating slightly in front.
It's up.
Okay, definitely the person will be floating slightly in front. I'd like you to also check, is your human being floating slightly higher than the actual height the person is standing at? Shall we try this together? Okay, good attempt. I see most of you are trying to work backwards. Number one, I see that the direction of the arrows have changed. That's a good thing. I also see that you try to extrapolate using dotted lines where the person might be. That is also a good practice. So you are nearly there. For those of you that find a little bit of trouble working backwards, let's try this question. So earlier on, I used the tip of the fish, right, all the way to the person's eyeball. But now that it's the fish perspective, let's start off with the top of the person's head to the fish's eye. So the fish needs to see the top of the person's head. So I'm going to draw this light ray traveling to the normal. Then after that, it bends in the water into the fish's eye. Okay, now the fish can see the human being. What's the direction it should take? The light ray should travel this way, so the fish can see the human being. Okay? However, the fish's brain is also tricked. The fish thinks that the human being, if I were to extend the light ray, the dotted line, this fish thinks that the human being exists not where it's supposed to be. I'm going to extend a bit more. So for your part, what you can do is to extend the light ray more. Okay? So I appreciate that most of your human beings are forward, but what you can do is you can extend the light ray a little bit more. Earlier on, we couldn't extend our light ray, our dotted line a lot because the fish is already quite close to the water. So I cannot extrapolate the dotted line very much. But for the fish, we actually can extend the light ray a little bit more in dotted form. Now the person appears to be higher. Okay. I like that as I walked around, I saw that you extended this particular light ray, the dotted line, on the way to the person's top of the head. I think the difference that we have is how far you extend that light ray. For the fish, the human will appear slightly further, slightly further.
It cannot see you. You see it?
Hold on, I think it's something about my diagram. My diagram will look very nice. I'm going to lower my image. this light ray.
Can see you.
Yes.
No, can see him.
No wonder. Okay, thank you so much. Confused myself. I wonder why my diagram does not work out. Thank you. Sorry, I thought this is a real human. This is a real human. It makes more sense now. Thank you. Okay, so once you're done with this light ray, okay, thanks for Ethan for saving me. So the next one you should draw is from the base of the human. You can draw a straight line all the way to the eye. So let's draw a straight line. But whatever is here, it should be on the way. Yeah, confusing myself. Hold on, let me think. Okay, for the second light ray, let me draw it orange. Your second light ray should start off, if you work backwards, it should be a dotted line. And then it should go straight into the eye of the fish. After which, we remember that the light ray bends from the actual human being. So over here. So you should have two light rays going in this direction. You should have two dotted lines, both extrapolating, one to the base of the human and one to the head of the human. Yeah, I tried to draw both light rays in different colors so that you can see the difference. One is slightly in front of the other. Okay, so this is what it should look like. Next, Ethan, I made a mistake of trying to connect to the wrong person. Okay, so to the fish, the human being appears slightly higher, but to the human being, the fish appears slightly. Okay, to the human being, the fish also appears slightly higher in the water. The fish also something the same place. Yes. Unlikely. Which thing? Oh, where to get it from? Oh, okay. So a question has been asked. We've been recording all our videos, right, of our lessons. How many of you know where to find the videos? Yeah, okay. So maybe Jack has the link to the website. Yeah, okay. Maybe Jack, you can resend the link. That link has an archive of all of our lessons since the start of the year. So if you want to revise, you can go and rewatch all the videos. I've labeled it as our class. Then after I labeled the lesson, like refraction, reflection, and so on and so forth. So for example, I know this was not the clearest explanation because I made a mistake along the way. But if you like to redraw along with us, you can rewatch the video. Okay? Okay, So we've done a little bit about apparent depth. The very last thing we're going to look at in your textbook to close off the chapter is on total internal reflection. May I get you to go to 7.4? I apologize that my phone has no battery. I honestly feel that if you see this in video form, you can appreciate it more. It looks very beautiful. Perhaps instead your iPads, do you have internet connection? Okay, so after I share a little bit about total internal reflection, I'd like you to go to YouTube. You go and Google this. It's really nicer to see it in real life. So let's look at page 16 of your textbook. We look through the paragraph. Total internal reflection is a very interesting phenomenon. This only happens when light is traveling from an optically denser to less dense medium. Let me illustrate an example. Let's say we have water, which is what's provided in your textbook, traveling out to air. We know that since water is traveling out to air, okay, let's do a quick recap. Okay, thank you. So if this is the angle of incidence, how will the light bend? Will it bend away from normal or will it bend towards the normal? Given that this is more optically dense, this is less optically dense, how will the light ray bend? Away or towards the normal? If you don't know, refer to page 12, the page that Rushi was talking about. As light is traveling from water to air, more to less optically dense, how will this light ray bend as it exits into air? Away or towards? Yeah, corner, yeah. Enjoy? What do you think? Away? When light travels from more to optically less dense, Enjoy is right, it will bend away from the normal. Yeah? So where's the angle of refraction? It will be this one. If I were to increase the angle of incidence, so let's increase it a little bit more. I have a new angle of incidence. This is a new angle of incidence. We expect that the light ray that's refracted will reflect more also, right? So let me draw one more light ray. Do you agree that this new angle of refraction will also bend more? Okay? Let's try it one more time. What if I have a third light ray? I increase up to this point. The interesting thing is, if the light ray is traveling from a denser to optically less dense medium, there will come a point where the light ray will end up traveling the surface and the intermediate of both media. Because if you keep increasing the angle of incidence, eventually the angle of refraction will end up to be just nice at the edge of the water. Yeah? If you keep increasing. But what if we increase beyond this particular angle? What if we increase beyond this particular angle? This is where this phenomenon called total internal reflection occurs. If we increase just slightly even more, the interesting thing is the angle of refraction will end up shooting into the water again. Reflection occurs if you expand this angle of incidence too much. So the term I would like to introduce to you is this. Can you highlight the word critical angle? You see your textbook on page 16, critical angle. They've also shown you the critical angle in your textbook, the middle diagram. They label a 0 with a small c on the bottom. Can you see the 0 with a small c? That is the critical angle. So on your textbook, you should see one diagram that shows you a light ray traveling like that. And then they label a C. Currently, this light ray, the refracted light ray ends up to be 90 degrees just on the edge of the water. What happens if we expand and go slightly beyond the critical angle? This particular light ray will end up bending into the water. And we refer to this phenomenon as total internal reflection. Because now this light ray is reflecting back into the water. We observe this only if it's traveling from more optically dense to less optically dense. Okay, I think it's enough of me talking. It doesn't look nice on the whiteboard. But I think in video form, if you see this happening in real life, it makes a little bit more sense. So can everyone take out your iPad now? I'd like you to go to YouTube. Type in these three words: total internal reflection. You should be able to find a video of a person using green lasers in water, and he demonstrates this particular phenomenon taking place. Have a look at this experiment. Yes, thank you. Okay, if you search, what are you sharing now? Okay, I think Ethan, he has found a very nice video. If everyone can turn on your AirDrop on your iPad, he's sending over the YouTube link. No lah, hey, you're not allowed to send these kind of things anyway. Okay, so if you turn on AirDrop, you should be able to receive a video link of total internal reflection. Exactly. Ethan, no, this is illegal. So those kind of content is illegal. Yes. Oh, okay. Then you still have to go to YouTube.
Android user, what do I search?
Total internal reflection. Oh, you don't have YouTube app.
Oh my god, I actually can't.
Then it's okay. Can we share? You mean it's got a video in front? Okay, but anyway, this is the last thing today. Watch the video that Ethan has just airdropped you. You should be able to see total internal reflection occur. Very beautiful. The light just reflects back into the water.
Oh yeah, this is for
Or you go to YouTube. Yes, correct. Go for it. Go to YouTube. We have YouTube. Oh, if it's your phone, use your phone then. Alright, I've already finished watching.
You know my phone, I think my iPad is mine. I did it on my iPad. I have screen time on YouTube.
Okay, this is good. I'll let your parents
I think my
put
iPad
limits.
is mine.
Total internal reflection.
But then you want Android to me because my iPad name is just iPad. So well, you want just iPad too. What's just iPad?
You see how the light ray will bend back into the water if you exceed the critical angle. Have you seen the video? Yeah, only have 12:30, so we will end here today. Tomorrow when I see you, we'll be going through your practical worksheet as well as 7.2.
They my back. Kan sekarang
What about other mother tongues? Do you all have tests also? Everyone has a test other time. Yeah, shall we all of you in English? The rest for your mother tongue exam. What kind of test is this? Oral, written? Sorry? Email writing? Is it email writing for everyone? You want to test your skills? No. Instead you email me in Chinese or in Tamil or in Malay. I'll just word translate over. Okay, last but not least, tomorrow your final script is due. For those that give me the script, I give you feedback. For those that didn't, then the first time I'll see if the final one I don't read it.
I don't know after I was waiting for you guys to
Yumi's group says
I don't mind. I'm not the good leader.
private group says. Sorry? If you want me to give, okay, because I can only mark, I will only mark the script, not the slides, right? The slides for the presentation. So, but you want to send me the presentation, it will be sent after the deadline. Yeah, but the script, you want to send, must send before deadline. Deadline is tomorrow, 2359. You don't like send me at 11 o'clock. Even if I give feedback, it's not going to save you. So, you need to give yourself enough time. I think warn you, so tomorrow I'll be at CCA after school from until around 7 p.m. So if you send it to me between 3 to 7, I will not reply you. But if you send before, there's still a chance I may. You send tonight, I confirm will stay up to reply you.
Yes, that is no problem.
You pay me more money. Go for another.